Hello, welcome to Chemistry Travels. So today we are going to look into an organic name reaction, which is the third reaction from the name reaction series. And the reaction is Baeyer Villiger Oxidation. So what is this Baeyer Villiger oxidation, or also called as the Baeyer Villiger rearrangement reaction? It is a very simple oxidation reaction proposed by Baeyer and Villiger. And it is the oxidation of what? It's an oxidation of a ketone, or insertion of oxygen in case of ketones. Ketones? Yeah. What would they react with? They would react with peroxy compounds. Ketones on reaction with peroxy compounds in presence of some Lewis acids or acid catalysts, they are going to get oxidized, or an oxygen is going to be inserted to these ketones, giving rise to esters. This is the simple Baeyer Villiger oxidation, where ketones react with peroxy compounds in presence of Lewis acids to give rise to esters. And if it is cyclic ketones that are involved, what are we going to get? In case of cyclic ketones, the same reaction would happen, oxidation or insertion of this oxygen to this ketone would happen, and you will get cyclic esters, which are termed as lactones. Right? So basically what happens here is, when I have a ketone like R, C, double bond O, R dash, this would be the ketone that I have. What happens is, at this near to the carbonyl group, the carbon-carbon bond, this here an extra oxygen gets inserted. So in presence of my peroxy compounds. So what are these peroxy compounds? They have an extra oxygen. They are peracids, like acidic compounds, acid compounds, COOH group, with an extra oxygen into it. Normal acid compounds would be like R, C, double bond O, O and then H. But instead of that, an extra oxygen and then hydrogen comes, OO groups. These are peroxy compounds, peracids, right? In presence of some acid, they are going to give rise to the esters, means an extra. At this carbonyl, the carbon-carbon near to the carbonyl group, that bond gets an extra oxygen, right? So the product is going to be R, C, double bond O, O, R dash. From here, extra oxygen gets added up. This is the simple Baeyer Villiger oxidation reaction. Right, clear? Now, let's look into what are those peracids that can be commonly used, that are commonly used for this Baeyer Villiger oxidation. Like I already told, peracids are normal acids with an extra oxygen or OO group. Like in case if I have R, C, double bond O, 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 H, extra, these are the peracids. So the common peracids that are found are, like for example, we can have peracetic acid, perbenzoic acid, then we have trifluoroperacetic acid, then the Carros acid, which is permonosulfuric acid, then what else? H2O2 hydrogen peroxide, that's also peroxide, as a common peroxide that we know. And then there is this metachloroperbenzoic acid. Right. So what is peracetic acid? Acetic acid with an extra oxygen. Acetic acid is CH3COOH. So we would have CH3COOH. CO 3 times H. Right. Or perbenzoic acid. Benzoic acid would have C6H5COOH. But instead of that, the same C double bond O, then OOH. Right. Perbenzoic acid. Trifluoroperacetic acid, which is CF3. Instead of the 3 hydrogen, it is replaced by fluorine. CF3CO3H. Or we have the permonosulfuric acid. Permonosulfuric acid can be H2SO5. Instead of H2SO4, which is sulfuric acid, we have permonosulfuric acid, which is H2SO5. And the most important one, or the commercially used one, the most used, commercially used one is perchlorobenzoic acid. It's easily available, and this is the one that is the most commonly used, and it can be seen in papers as MCPBA. Metachloroperbenzoic acid. So it's just that my benzene ring is there with C double bond O, OOH, and at the meta position I have my chlorine group also. It's like metachloroperbenzoic acid or MCPBA, and this is the most commercial one. Apart from that, we have peracetic acid, trifluoroperacetic acid, perbenzoic acid, or permonosulfuric acid, or H2O2. Okay. So now that we know what the reaction is, what are the different possible peracids that can be used, now it's time that we look into its mechanism. As we know, mechanism happens to be something very important in predicting the products of reactions in organic chemistry, right? So let's look into the mechanism of this Baeyer Villiger oxidation. It's a very simple mechanism, nothing complex about it. So for this, let me consider a ketone. I'm going to consider a ketone, which is R C double bond O R1. Okay, this is a ketone that I consider. So first what happens is, in the first step, my Lewis acid that I told, the acid catalyst that I have, H plus, that comes into play. Okay, H plus is there, that reacts, and obviously the oxygen is gonna abstract this H plus, this Lewis acid. My oxygen is gonna abstract this Lewis acid, right? And what is the product that I come up with? R C OH R1, right? After the H plus being abstracted by the oxygen, the product that I'm going to come up with then is RCOH R1, and the carbon, because its bond is broken, the electrons are given off to oxygen, the carbon is now positively charged. Now that my carbon is positively charged, here comes the play of my peracid compounds, peroxy compounds, or my peracids. That is where that's gonna react. Now what is my peroxides? It will have some R2COOH, something R2C with OOH. This is the thing that is going to be there. So definitely this oxygen will also have lone pairs of electrons which it can donate to that carbon. So what happens now? This hydrogen would go off and this oxygen is going to bond with this carbon, right? The carbon of my ketonic group, which has become positive after abstracting the hydrogen, now that would react with the peracid compounds. And what is it that is going to happen? My RCOH R1 is there to this positive charge carbon. Now this comes up. oxygen, oxygen, C double bond O, R2 is same as that, right? Now what happens? A 1,2 shift will take place, and R group or methyl, that R group can actually shift. Some shifting takes place. And what happens as a result? This would be given here, and this whole group, which is that this whole R group is gonna shift to this oxygen side. Okay. This bond, oxygen-oxygen bond, is now going to cleave, and one oxygen is going to go out with the remaining group, and from the ketonic part, one of the R group is going to come and join to the oxygen. So what is the product that we are going to get? The intermediate product is R, C, OH. Now that this R1 has shifted to oxygen. So oxygen was there and R1 has shifted there, right, to this oxygen, that I've written straight like this. And what has come out? This particular group, this whole group has come out as minus R2 CO O, with this bond also it is CO minus. This has come out, right? So this is the group that we get. Now what happens further? Because this has shifted, this carbon is now positively charged again. The group that was attached to this carbon has shifted to oxygen. So now the carbon has become positive again. So what happens? This hydrogen would go out as minus H plus, right? This OH group's hydrogen would give out, the bond would be broken, OH bond would be broken, H plus would move out, giving rise to R, C. Now it becomes double bond O, OR1 is there as usual, and this is my ester, which is the final product. I started with a ketone, and initially the Lewis acid came into play, giving rise to OH group, alcohol group from the ketone, which further reacted with the Baeyer acid because there was a protonated, there was a positively charged carbon. And after reaction, a shift takes place between the R group and oxygens and all, and OO bond is breaking, and one of the oxygen is going out as R2COO minus, and the remaining portion is left behind. And to that oxygen, now one of the R group is attached as a shift has taken place. And now that again that center carbon becomes further positively charged, so H plus would go out, giving rise to my final ester. So now we know the mechanism, right? We know the mechanism, but there was one thing that was left out. Like the ketone that I considered was R, C, double bond O, R1. This was the ketone that I considered in the mechanism, and it happens that either this R can shift or this R1 can shift. In the mechanism, I showed by shifting R1. But when there are two different groups, there is a possibility that sometimes this R can shift its position and join with the oxygen, or my R1 can shift and join with the oxygen. So which would shift faster? Which is the migratory aptitude that we are to look into. So let's look into the migratory aptitude. Of the ketones, right? If we have to look into the migratory aptitude, we can say that the migratory aptitude follows as tertiary alkyl group is the most predominant, or it would prefer migration faster compared to cyclohexyl groups in comparison with secondary alkyl groups and then comes benzyl or phenyl, which has almost similar migratory group, and then I have my primary alkyl group, and at the end last I have my methyl groups, which has least preference for migration. So the migratory aptitude follows as tertiary alkyl followed by cyclohexyl, secondary alkyl, then comes benzyl or phenyl having the similar migratory aptitude followed by primary alkyl, and finally the methyl. Now if I consider the case of aryl groups, if it's the case of aryl groups, these are for alkyl groups, right? So if I consider the case of aryl groups, what happens? They can have electron withdrawing groups or electron donating groups, and electron donating groups, they favor migration. Why? Electron withdrawing groups, they do not favor migration. Okay, so this is a common order, and in case of aryl groups, it is the electron donating groups that cause the migration, and electron withdrawing groups are present means they would not cause the migration of that particular aryl group. Clear? So now let's try to apply this migratory concept to this equation, to this particular question, and try to find out what the product would be when this particular cyclic ketone is reacting with my peroxy compound, which is that trifluoroperoxytic acid in presence of Lewis acids. Let's try to find out what the product would be. See, there are two possibilities in this. If you look at this, you will understand that near to the carbonyl group, either this carbon-carbon bond can break and oxygen can come in between, or it can be that this carbon-carbon bond can break and oxygen can come in between. Two possibilities are there. Now, out of this, which is a group which is going to migrate? The left side to the carbonyl group or the right side to the carbonyl group? Which group is going to actually migrate and give the product? So, based on the migratory aptitude, let's write down the mechanism and see what's going to happen. Okay. So for that, let us first step mechanism. If I am writing down the mechanism, I'll write down the reactant once again. C4H9 substituent is there. This would first react with my Lewis acid H+. This was the first step. So this oxygen is going to abstract this proton, right? And what is it that I'm going to get? An OH here. The C4H9 is there as such, right? But because of this shift, now this carbon becomes positively charged. Now that my carbon is positively charged, here comes the play of my which group? My peracetic acid group, trifluoroperoxytic acid, which was HOOCO CF3. This was the group, and that is going to come into play. And now this oxygen would bond with the carbon atom, and what is it that we're going to get? OH is there as such. Apart from that, there is O, and the C4H9 group is also there as such, right? This is what's going to happen. Yeah. Now what happens? The shift takes place, right? That is, either two possibilities are there. Now, this is going to shift. This is definitely going to shift. And what is going to bond with the oxygen? Either this group can shift to oxygen or this group can shift to oxygen. Two possibilities are there. So out of the two possibilities, if you look here, you will find that this carbon is secondary while this carbon is tertiary. And we already know that tertiary has more preference over secondary. So in that case, it is this tertiary group which is going to move towards that oxygen. And once that happens, what is the group we are going to get? This extra portion is going to come out. That CF3, C double bond O, O minus is going to come out, and the remaining, what after the shift, what we're going to get is, this is there, all this is there as such, and extra oxygen comes in between. The bond now has, from here it has shifted like this. So this is an extra thing. This OH is there as such, and this C4H9 is also there as such, right? So that has happened, and because the shift of this bond has taken place, that carbon will now be positively charged. Now that the carbon is positively charged, from this OH group, H plus would again come out as minus H plus, and finally what we are going to get is double bonded O there and C4H9. So starting from a cyclic ketone, I ended up with a lactone, and what we can see that tertiary had a higher preference or migratory aptitude compared to secondary. Because of that, it was this bond that was shifted. This particular bond had shifted and gave rise to this product. Clear? So here are some more questions, like 3 more reactions are there, where you can actually write the whole mechanism and see whether the product is being formed, how the product is being formed. But let's just, instead of writing that whole mechanism, we can just simply insert the oxygen also, right? So we know that carbonyl group is there, so either this side or oxygen can be formed here, or if you write the whole mechanism also, you will understand that either oxygen would come here or oxygen would come here. But since this system is both sides the same, it's symmetrical, so it doesn't really matter, and the product is just going to be a very simple thing. An extra oxygen is also added up. That bond was broken and an extra oxygen group was added up there. Same goes for the other 3 examples also, like here also. Now it would be either this side which is breaking or this side which is breaking, that carbon-carbon, and oxygen would get added up. But this is tertiary, this is secondary, so which has more preference? This side has more preference. So what would be the product? Here actually it would break up oxygen an extra oxygen atom got added up there, right? That bond broke and extra oxygen got added up there. Now this also some, okay, CH3, some trifluoroacetic acid or some peracid is there, and what happens? This is methyl group and this is the cyclic group we have. This is a methyl group, and we know that methyl has a very low preference, right? Its priority or its migratory aptitude is very low, so it will not undergo that movement transfer. So oxygen is actually supposed to come and break this bond. This carbon-carbon bond is where it is cleaved and oxygen is getting inserted. Because of this, it's lower priority compared to this side. So what is the product that we're going to get? It's just that we are going to have an oxygen here. The remaining, it's the same thing. So this would be the ester group that we are going to get from this particular reactant. So you can actually write down the mechanism and see if it works out, and you're coming to this particular products. Okay. So I guess you understood this concept, and that's it for today's video. Thank you so much.